Hello, this is Guillermo Campitelli, and in this video is about multi-level models. So I'm going to show a case study with observational data in this video, and in the second video I'm going to present a case study with experimental data. So multi-level models were developed for observational data, which typically is collected at different levels. And I'm going to show that with my case study very quickly. So in this case study is about academic achievement. We've got 1,200 participants, and those participants belong to 16 schools, and the schools belong to 4 regions. We've got predictor variables: region, income, student-staff ratio, study hours, intelligence, and sex, and one outcome variable, which is academic achievement. So we are trying to predict academic achievement using those variables. Now those variables are collected at different levels. So region income, it's at the region level. So it's the average income of the region, and we only have 4 values. Student-staff ratio is the student-staff ratio of each school. So we only have 16 values of student-staff ratio. Now study hours is collected at the participant level or the individual level, and so we've got 1,200 observations there. Same intelligence and sex, they are characteristics of the participants, so we've got 1 observation per participant. And the outcome variable is also collected at the individual level or participant level, and we've got 1,200 participants. Now this is when we've got this structure of the data, we've got problems. So how do we, if we want to use the whole data, how do we use the data of the variables that was collected at the schools and regions levels? Do we use 16 values? So, and we repeat those values for the participants that belong to the same schools, and the same for regions. We've got 4 values, and we repeat those values for each of the participant who belongs to that region. That is problematic because these values then will enter into the into a regression, let's say, and then not only they are not independent, but they are the same values repeated. So that's really bad. We cannot use a traditional regression to analyze those data. So what people did in the past was, well, there were several things that they tried to do, but sometimes the most popular was to, if we want to analyze the effect of region income on participants, then we are going to use that analysis separately from the analysis in which we investigate the other variables. Same for student-staff ratio. If we want to investigate the role of student-staff ratio on academic achievement, we use those 16 values, and we don't use the 1,200 participants. We only use the 102,000 participants when we investigate the role of study hours, intelligence, and sex on academic achievement. But is it possible to analyze the data on the same analysis? Well, multi-level models were created to do that. So multi-level analysis takes into account that the data was collected at different levels. So here is the 3 levels in this case study. We've got the level of the individual or the participant, the level of the school, the level of the region. So we've got number of individuals who belong to the North Rough School, and the North Rough School belongs to the North region. We've got other individuals who belong to the North Upridge School, and this one to the North region, and so on and so forth. So we don't show all the categories within each variable, but that's the idea. We've got data at different levels. So the model of the study is we use these 5 variables to predict academic achievement, but we know that these 2 variables are collected at a different level than these 4 variables. Okay, so first of all, let's look at some descriptive data. So that's the data that we obtained with Jamovi. So we are going to use Jamovi, and I show you how we get the descriptives. Okay, so here we've got the data set with 1,200 participants, and now we are going to get the descriptive statistics. Okay, I'll show you 1,200 participants. So exploration, descriptives, and then we put the variables that we are using in this study. We've got intelligence, study hours, academic achievement. Then we've got the variables at the region level, income per region, and then at the school level, students to staff ratio. Okay, so we've got here the table with the descriptives: mean, median, height, cost, statistics to what the standard deviation, tick over there, and it appears there. Okay, so these are the variables we are interested in. Now I can put also gender or sex. Let me see what it is here, and sorry. And sex, it tells me that only that there are 1,200 cases because it's a nominal variable. Okay, but if I do frequency tables, it will show me, okay, so I don't want that for the numerical variables, but for the nominal, I want to have these. That tells me that there are 582 females, 608 males, and the percentage of each category. Okay, now what I can do now is I'm going to go to the academic achievement variable, and just not use the others. So I'm interested now on the outcome variable of the study. So we got that, and I can create plots by going to plots, and I want plots with the data, and here is the plot. I can do violin plot, or I can do the box plot. Both is not good, so that's the data, and I can do a histogram as well. Okay, so that's the graphs of academic achievement. Now I can split by region or split by school to see whether the distribution or the statistics are different in each region. So here I've got the mean of academic achievement in the whole sample of 1,200 participants is 50.5. Well, I want to know whether we've got the same mean in each of the regions or each of the schools. So I use split by. Let's do it by region first. Okay, so that takes a bit of time. I've got the data. So for region East is 51.4, region North 50.9, region South 49.8, West 47.6. So there is a difference, not great difference, but maybe it's important to take into account that for the study. Okay, so we can do plots of the regions. Okay, I didn't do anything because it was already ticked, and the Jamobi did the histograms. So we can see that there are differences, but they're not very different. And here we've got the data of academic achievement in each region. Okay, so we can do the same but for schools instead of region. Okay, obviously it will be much longer because we've got 16 schools. And let's see if we can. So we've got all the schools there, the histogram for all the schools, and we've got here the box plots with the data for each school. If I want to get a graph that showing the number of people in each school or in each region, then I put school not in split by, but as the variable of interest. So let's put school there actually, and then I get the frequency tables, and these are the frequencies because we are not going to get all these. Applies only for numerical variables, not for nominal variables. So if we take the bar plot, because these don't count for nominal variables, so bar plot, it will create a bar plot indicating how many people are in each school or belong to each school. So we can do the same with regions, region in variables, and we get the bar plot for regions. So here is important, we tick frequency tables. If we don't tick frequency tables, we don't get this table. We just get this. And the plot is the number of people in each region. So this is unbalanced. There is not the same number of people in each region, which is typical of observational studies. Okay, let's go to the slide to show these were the descriptives I obtained. That's the table I obtained for frequencies in each school. This is frequencies in each region. That's academic achievement in the whole sample, the histogram of academic achievement in the whole sample, histogram of academic achievement in each region, and histograms of academic achievement in each school. Okay, so let's now start explaining how we do the multi-level analysis. So first of all, I always like to start with a very simple model, which is the simplest model you can think of. So in this, remember that for models we always have two parts of the model. One part which is an equation that determines the value of some mean, and then this what we call stochastic part of the model, which is non-deterministic, and which shows how tells us that the way we predict each value of academic achievement is with a normal distribution, and that distribution has a mean, which is mu I, and a standard deviation sigma. So basically, because we have the subscript I, and I here represents the individuals, that's a shortcut for 1200 equations. So it's telling us, or rather than equation formulas, so it's telling us that the value of academic achievement for each participant is normally distributed with a mean of mu I, which is 1 per participant, and one standard deviation sigma, which is only 1 for the whole sample. It doesn't have the subscript, and it also this part of the model tells us that the mean that is here, it's equals beta 0. So beta 0 is a parameter that we are going to estimate with the data, but that shows you something that is important. Beta 0 is only one value, so this formula tells us that all the values mu will be the same, because if they were not the same, then we should have a subscript I here, and we don't. So basically it's a very bad model, because we are going to predict the whole sample of values of academic achievement with only one value, and these we can only do it in Jamovi using a trick. So I'm going to show you the trick. And the reason why we need a trick to do this is that typically we are not interested in this model. It's too simple. But I like to show this model because I want to say that any model that is a good model has to be have a lower AIC than the AIC of this model. And so the trick I'm going to use is that if you consider that this formula, actually this should be a plus and not a multiplication sign. Okay, now I corrected this. So I created a variable that is called ones, and basically for the 1,200 participants I put a number 1 to each of them. So basically if you consider that so if you consider that beta 1 is the effect on academic achievement, or the mean of academic achievement, with a variable that doesn't change, well, this value is the same as this value. It's not a nice way of doing things, but I just have to do it because otherwise, if I just use this, which is a perfectly okay model, Jamovi doesn't like it. So I show you, if I put academic achievement only, I don't get anything. So Jamovi doesn't do anything. But if I use the ones covariant, then it calculates it makes an estimation, and as I said, the beta 0 and beta 1 are the same. So basically that's a trick to get the estimate and to get the AIC. That's the most important thing that I wanted, to get the AIC, which is 7,700. And I show you again how I did this. So you go to linear models, and I go to generalized linear models. Why not general linear model, which is typical regression? Because it doesn't give me the AIC if I go to general linear model. So that's why generalized linear model. For the multi-level analysis proper, we are going to use mixed model. I'm going to show you that later. But basically, obviously, if you see the mean of academic achievement, the mean is 50.5. So I knew that the intercept is 50.5. I didn't need to do this, but I wanted to get the AIC. That's why I did this trick. Okay, so we've these are the results. The beta 0 50.5, and the AIC 7700, and this beta 1 is ignored because it doesn't make any sense, just a trick. Okay, so now that's the reference model, and any model that we propose should be better than this. So in this model we are saying that academic achievement, the values of academic achievement observed in this sample are not explained by any variable. Okay, so if we want to establish that there is an effect of a variable on academic achievement, then the AIC has to be lower than 7,700. Okay, so let's incorporate what we call the random intercept model. Okay, that requires a very detailed explanation, so I'm going to go slowly. So first of all, we've got a difference with the previous model, in which the mu now is ij, so it has two subscripts, and the I stands for the individual, and the j stands for region. So we've got, this means that now we are going to have a mu for each participant who belongs to each region, but there is no, so now the equals here is beta 0j, so it means that we are going to have 4 beta zeros, 1 per region, but we are not going to have 1 per participant. So basically the participants will have the beta 0 that belongs to their region. And then the distribution we use for determining, for making the prediction of each value of academic achievement is a normal distribution with a mu per participant per region, but this formula says that we are going to have only 4 mu's and only 1 sigma. Now, the added value, the thing we add here is as well is that beta 0j comes from a deterministic formula, which is gamma 00 plus u0j. Now, gamma 00 is the mean academic achievement in the sample. So, mean academic achievement in the sample. And uoj is the difference between the mean of a region and the mean of the sample. Let's say that we know that the mean academic achievement of the region is 50.5, and then if we add the difference, let's say, let's have one region is 55.5, the mean. So 55.5 minus 50.5 is 5. So the U of that region is 5. So basically, for each region, the beta 0j is the mean of the sample plus the difference of between the mean of the sample and the mean of that region. And then we say that this difference comes from a normal distribution in which the mean is the mean of the sample, mean academic achievement of the sample, and then lambda, this Greek word lambda, which is a standard deviation of, or it could be the variance of the normal distribution, and we are going to estimate that value with the data. Now, what we are going to do actually is very similar to an ANOVA, a one-way ANOVA with 4 for categories within the nominal variable region. But in fact, we are not going to do exactly that, because if we did that, what we do is to calculate a the mean of each region and obtain the difference with the mean of the sample, and these are 4 parameters, so 4 differences that we need to calculate. In this case, it's not a problem. 4 parameters with 1,200 participants is okay. But if we have more complex models, and or for example, if we're talking about schools and not regions, school we have 16. So we've got to obtain a difference per school, and that would be 16 parameters. And so, as you can see, we are adding parameters, and the more parameters we have, the more penalty we get in the AIC. Remember, AIC receives a penalty for adding parameters. So we want to have a model that estimates academic achievement, predicts academic achievement with less parameters. And the trick is doing this. I'm not going to be interested in the UOJs because we need 4 of those, and I'm not interested in the beta 0Js because again there are 4. I'm going to be interested in these, the mean and the lambda, which is the standard deviation or the variance, depending how we want to report, but they are equivalent. They are proportional, not equivalent. And we can choose which one to report. So we instead of having 4 parameters to estimate with the data, we estimate 2. Now 2 versus 4 is not much of a gain, and why make a complex analysis not to gain a lot? But if we consider schools instead of regions, we would have to do 16 parameters, and it would be exactly the same for in the multi-level analysis. We estimate exactly the same number of parameters than if it were for regions. So basically we've got 2 parameters instead of 16. So that is a very important gain, and the model will receive much less penalty. So that is so basically in terms of why we do that, basically the rationale of this model is that the intercept of this regression, we've got one intercept, which is the gamma 0, 0, which is for the whole sample. And then we've got, if this lambda is high, that means that there is a variability in the intercept. So the intercept, if we calculated an intercept in each for each region, then it will be very different than, or there will be some difference with the intercept of the sample. If the lambda is a very small value, it means that all the values, all the intercepts in all the regions are very close to the gamma 0, 0. So these two parameters are the ones that we are going to be interested in. And for Jamovi, we have to make the same trick as before. We use the variable ones, and now the parameter beta 0, we've got 4 instead of having 1. Okay, but importantly, we never report the betas here and the u's. We never report that because that would be to be reporting that we are estimating a lot of parameters, but in fact we are interested in this parameter, the gamma 00, and the lambda, and obviously the sigma that it's to predict academic achievement in each participant. Okay, so I'll show you how we do that in Jamovi. So now we are going to do multi-level. So multi-level we do mixed model. So before we use generalized linear models to obtain the AIC of that simple model, and now that we added what we call random intercepts, then we need to go a mixed model. And now we are going to use this once variable, just because it's a trick. We use X covariate. We add academic achievement as the dependent variable or the outcome variable. So academic achievement. And we don't have any other covariate. Now, if you go here, go to fixed effects, it automatically put one of the variables. And in random effects, you have to indicate the random effect. Okay, I forgot to add a very important part of the model, which is what is called the cluster variables. Basically, that's the levels. So if we want to put to get a random intercept like we want now, for region, then we have to add the variable region here. And if we want to do it for the variable the level school, then we add a school here. So we are going to do it with region. And now we see these are the fixed effects. We've got the ones, but that's as you know, is a trick. And now we can add these components, which we are going to add the intercept conditional on region component. So basically, that is going to indicate that the intercept, if the lambda we obtain is large, and the AIC of the model is lower than the previous model, then it will indicate that there is a variability in the intercept of the regions. So for the 4 regions we have, the intercept would be different. Obviously we are not interested in ones, so we don't add that. Now this takes a bit of time, so be patient. This model still is okay, but more complex models will take more time. So in the video I'm going to edit in order not to wait. But when you do it, don't worry that you have to wait. Don't panic. The Jamovi will do the analysis, but it takes time. This is because there is a lot of simulations, Monte Carlo simulations going on in the background. Okay, so for this model we've got the AIC 7667, so it's lower than the previous one, indicating that the intercept of the regions is there is a variation. And okay, so basically the estimate of the intercept is 50, and then we've got the this is called the region intercept, which is we are going to talk about the variance, but as you can see, Jamovi also reports the standard deviation, which is this. We are saying that the intercept of each region comes from a normal distribution in which the mean is the fixed effect of the intercept 50, and a variance of 2.56, or a standard deviation of 160. These are proportional numbers. And the residual is okay, so when we make the prediction for each participant, that prediction will have an error, and that error is we can represent that with a normal distribution in which the mean of that distribution is the prediction of the model for each participant, and the variability is the standard deviation is 5.88 here, or the variance is 34.58. Okay, so these are the values that I've got here, in the results. This is the fixed effect, or the fixed intercept. It's one of the fixed effects of the model, and it's 50. Now, this is a bit different than the mean of the sample, mean academic achievement of the sample, as I indicated before. And the reason why there is a difference is because the regions do not have the same number of participants. So then the mean of each region has a different weight. The regions with more participants or more individuals, they will have a more important input into the model, more weight into the model. So that's why you are going to see that this fixed effect in all the models will be very close to 50.5, which is the mean of the sample, but it's not going to be exactly 50.5. So that's the variance, 2.56 of lambda, and sigma 35.58, and this is the AIC. Every time you run the model, the AIC will be slightly different, so don't panic if you have slightly different values, but basically the difference here is it's like 80 points, 33 points here. 7,700 was the previous model, so 667, that's the difference of 33 points. Okay, so that means that because it's a lower AIC, this model is better than the previous one. That means that incorporating a variability in the intercept means it improves the model. So we are going to keep this parameter, which is the variability among regions, and we are going to now make more complex models, because so far we don't have a predictor variable. We've got a level, which is the regions, but we don't have variables to predict academic achievement. So let's now add some variables.